Let's do the sixth and final lecture on climate change. Up until now, we've been going over scientific process with respect to CO2, greenhouse gases, and absorption with energy, and then also data and how we have built observations like the Keeling curve over the last 50 to 100 years. Well, today now we're going to say, what was the point of all that? Well, it's to feed it into models and then allow those models to make predictions for the future. And the key with models is that they could be right, they could be wrong. They should be developed for guidance. They should be developed with prudence. They should be made for protection of society or for a nation, for finances with insurance companies, okay? I want to make sure that these concepts are built in when you think of the word model. The other thing I want you to think about with model is uncertainty, and I'm going to take time to write that down with my best penmanship. Uncertainty. Each of the predictions I'm going to show you have an uncertainty. Some of them are low uncertainties. We know with pretty good degree of confidence that this prediction will come to pass. Others have a significant knowledge gap and there's a large degree of uncertainty. The other thing I would like to point out here at the beginning is not everything follows prediction. Sometimes people win the lottery, even though it's statistically impossible. And there are things like that in nature that we might not be able to predict. The next thing here as we get started is that these predictions are coming from IPCC, which is the International Panel on Climate Change. They recently came out with their sixth assessment, which is a 2,500 page summary of the state of the art in the science. And it is an incredible bit of science. It has been written for lawmakers so that nations and industry leaders can make the best decision based on the data that has been collected up till now. So this is the source for what I'm going to show you. And within this IPCC 6th assessment, there are dozens and dozens of models that have been tested, refined, benchmarked against one another, and benchmarked against observations from the past. So I'm going to start here is with 3 graphs. And this is to kind of summarize what the IPCC result is. And one of the biggest players in this is gigatons of CO2 that's been produced by society. And this x-axis is going to be time in years, and here is today, and then this is moving into the future where you will live and die, where your grandchildren will live and die, etc. And we're trying to make a prediction until then. And this prediction can be good or it could be bad. What if society increases its amount of CO2 emissions and then technology allows it to decrease with time? That is one of the scenarios that is being predicted. Okay, if I can change my color of pen, come on. Another prediction could be that our society continues to make CO2 and at an outrageously rapid pace. Well, the prediction for these, the models, would be different. And so if we have a lower CO2 society in the future, what will our atmosphere look like in terms of ppm CO2? Well, it may increase with gigatons emissions, and then it may start to go down. Or we could have that red scenario, and the amount of CO2 could increase past 420, past 600, past, up to 1,000 ppm. The impact of the red or the black curve is going to be very different. All right, there's different implications for each of these. And one of the things is, what is nature's response? So nature's response can be different depending on where you live and what aspect of nature we look at. So for example, let's look at this scenario here, this low CO2 future, which I think a lot of countries are aiming for based on the data. With a low CO2, okay, so what is this? This is going to be now temperature on this graph in degrees Celsius. Here we are today. Well, if CO2 increases, then our atmosphere temperature is going to increase, and as CO2 goes down, we think it's going to go down. And this is with a fairly high degree of certainty. This lag between when the CO2 shuts off to the atmosphere and when CO2 goes down, this lag in terms of atmosphere is on the decadal scale. Let's say like 10 to 30 year lag. But that's not true for everything. Oceans, for example, have significant heat capacity. And so we believe that the natural system of the world's oceans are actually going to have a lag time where they're going to increase in their temperature and therefore their thermal expansion for a long time, even after the CO2 decreases in the atmosphere. And the estimate in these models is something like 300 years. So the point of this is society will respond in some way, and we're not sure what it is. If it goes in X or Y, nature will also respond. But nature's response has a different time period. To anchor the notes down a little better, I want to go through predictions for nature's response. And there are probably 100 different predictions we could make with a variety of different levels of certainty. And I want to just give you like the top 6 or 7 here that I think are significant and have a higher degree of certainty. And the first is that temperature will increase over the next decades to centuries, depending on how society and its economy behaves. Here's the graph from the IPCC. And what we see here is this is the cutoff on the graph between what is observed and what is predicted. And the predictions show it doesn't matter which model you use. Yes, there's a degree of uncertainty, but the models all seem to agree that temperature will increase at a fairly steady rate. The rate is generally 1 degree C per 1,000 gigatons of CO2, right? So here we are, this is 1 gigaton of CO2, and the increase, right, rise over run is around 1 degree C. This varies between 0.5 to 2.5, but most models show around 1 degree C, and it's fairly linear. The next prediction that is fairly high degree of certainty is that precipitation will increase. Precipitation will increase. It will increase because ocean evaporation will increase. Okay, so let's maybe say something like ocean warmer. Also, the atmosphere is warmer, and because it is warmer, there is more evaporation. Evaporation then puts moisture into the atmosphere, which then will increase the amount of precipitation, right? This evaporation is the fuel for more precipitation. Now, the key to this precipitation increasing, though, is that it is not going to happen the same everywhere. Here is one of the models in IPCC, and what you can see in this graph is these blue colors are wetter areas, and here are drier areas. And so from this prediction, which was like that temperature would be up 3 degrees Celsius, like 50 years from now or 100 years from now, well, the model would be that some areas of the world, like here, would be wetter, but then other areas of the world will be drier. And so I happen to live in Texas, so this projects that Texas would actually be a little bit drier in this scenario. This is hard to predict. The climate system is very complex. Things like the jet stream and El Nino, La Nina cycles are all involved in this. But in general, precipitation will increase. It will not be even. Let's put that. Not even, right? That's what this is showing. Some areas wetter, some areas drier. And another thing within this is that extreme events will be stronger. Extremes, we'll say more extreme. Storms will have more precipitation, but then droughts will even be drier. Number 3 is that climate belts will shift. Climate belts shift. This is going to be for both latitude and altitude. As you go to higher latitudes, that means more and more towards the poles, you get colder. Well, warmer climates will head towards those poles, and then also as you go higher into a mountain, it gets colder, and so altitude, you're going to get these climatic belts to shift. If climate is shifting, the plants and animals are also going to be shifting, and so biology migrates. Biology migrates, and I want you to notice one thing here, is that temperature increasing is directly impacting climate belt shifting and biology migrating. The predictions impact one another. So as biology migrates, then the other effect of this is, there's going to be different examples of this, both for good and for ill. One of them is going to be leading towards biodiversity loss. Some biodiversity, like the polar bear, may not be able to exist anymore in a warmer world, and so this will lead to extinction. And we are at a time period with some of the very high extinction rates, much higher than background levels. But the other thing that could happen as biology migrates is that we have longer growing seasons. And so there will be some areas near the poles, let's say Canada or Russia, where, again, this isn't biology, this is more agriculture, but the same is true for biology, is that near the poles, you'll have a longer growing season, and so maybe more biology could be existing. Number 5, permafrost melts. So as climate belts shift near the poles, things are getting warmer, and we can melt permafrost. Let me show you what I'm talking about here. So here we are looking down on the North Pole. Here is Greenland, right here is Russia, here's Canada, and this measurement here is carbon in the soil. Permafrost is soil that's frozen. And if that soil is able to melt, then the carbon in it will be able to thaw. The carbon is in organic material, dead plants and leaves. As carbon thaws, it can then decay. So we'll go carbon thaws, then we can say carbon decays. And when you get carbon decaying, you release CO2 plus methane. And so this would be a natural source of greenhouse gases, estimated around 10 gigatons per year, which is a significant amount compared to the 59. So there is an uncertainty here. Will it unfreeze? How much will it release? But if it does, we know that it will release an amount naturally to the greenhouse gases, which then would have an impact on temperature, right? A positive feedback potential. All right, number 6 is sea level rise. Sea level rise is a direct observation we're having, and of course projected into the future is a fairly safe bet. The amount of sea level rise into the future is somewhat unknown. The amounts range between, let's see, so where is that over here on the, so this is time, here's meters of sea level rise, so that's 1.5. Down here, this is 0, so right, so somewhere between 1 to 5 feet, maybe 30 centimeters up to 1.5 meters. So on the order of a few meters. Should we put that in? Well, the graph, I guess, is already showing it. The reason for this sea level rise is twofold. It's from ice melting, mostly the ice sheets on Antarctica and Greenland. If Antarctica were to melt fully, that would be 60 meters worth of water contributed to the oceans. Well, that's a lot more than what we're predicting here. We don't even really know how Greenland and Iceland will respond, but melting is probable, and that meltwater goes into the oceans to make it deeper. The other thing is thermal expansion. As oceans warm up, they thermally expand, and that can make the oceans deeper and therefore doing sea level rise. The final point here is that the oceans are going to become more acidic. So oceans acidic. And this is the reaction we talked about in one of the previous videos. As you have more CO2 in the atmosphere, that CO2 can be absorbed by the ocean, which makes bicarbonate plus H, and this H is our lower pH. And this is going to impact the biology, right? And could lead to biodiversity loss. There is uncertainty here because it's a complex system, but in general, I think oceans will become more acidic. So to finally wrap up this video, I just want to leave you with 3 more words. And this is technology, this is government, and this is private. These are all ways, right? This is the private business sector and the private individual. What do governments do, both in the United States and around the world? And what can technology do? Technology moves with gradual transitions and disruptive transitions. We don't know what technology will be developed, but technology definitely could change these predictions and how we live in a world with more greenhouse gases. Government can impact things like taxes and like land use and investment. Depending on where you are in the political world, you may decide what role government should have in doing these things. And different countries around the world have their government impacting in different ways. The other thing here is in the private sector, what can you personally do? And then also, what can companies that are, the Apples and American Airlines, what are these big companies going to decide to do with the resources that they have? So we could say personally versus like the big money corporations. These are the big players, and we're not really sure. And then maybe the last thing to think about is if we tie all these together, we're getting into this thing where what is the societal agreement, and can we have one? I actually don't think we can, because our cultures are so diverse. Our beliefs are anchored in traditions, religions, connections with the land that produce a worldview within us that is very diverse. But maybe, hopefully,